Okay, welcome back everyone. In today's video, I'm going to be making the continuation video of um, Euler's great formula. This is part 2. Okay, and here are our tools. We have the Maclaurin series for sine, cosine, and e to the x. Now the first thing I want to start off with is what happens when we look at the series, infinite series e to the ix, where I being the imaginary unit. So let's see what happens there. And note that in order to find e to the ix, we just plug in ix for x here. This is merely just a placeholder variable. And note that we also showed that all of these, the radius of convergences of all of these is infinity. Thus, for all x, these Maclaurin series representations will hold. So let's begin. So e to the ix. So we could directly plug it in here, but it'll help, as we'll see, it'll really help if we actually find some terms. So imagine we plug this in and we compute some terms. So for n equals 0, we clearly still get, we still just get 1 here, clearly, right? Because we plug in 0 here for basically, we plug in 0 for n, we get a 1 on top, then we plug in, because ix to the 0 is clearly going to be, 1, and then over 0 factorial is just going to be 1, so we have 1. And then what we have is, plug in 1 here, we get ix over 1, so we get plus just ix, okay? And then what happens next? Well, now what we get is, it gets a bit more interesting, because if we plug in n equals 2, then note that I squared is negative, so we get minus x squared over 2. So as you can see, this is starting to look, maybe it's starting to look a little bit familiar to some of you. And then how about the next term? So basically I cubed. Now I cubed, what happens if we multiply negative 1 by I, basically? Then we get negative I, so we still get minus here, so we get minus basically I x cubed over 6, because we're plugging in for 3 factorial here. And for the next term, let's just keep going. We will get a plus, right, because we're multiplying, we're actually multiplying negative I by I, and I times I is negative 1, so we get a plus 1, and then we get x to the 4th over 24. Okay, and it should be pretty clear now that we'll get an alternating series, but not just any alternating series. It's kind of like a two-piece alternating series. It's plus plus here, minus minus here, plus plus here, and so on. So this goes on forever. And you see, maybe you might consider collecting some of the terms. Okay, what if we collect all the terms with I in them, and so we'll collect all the real terms with each other and all the imaginary terms with each other. So this equals, okay, so let's collect all the real terms first. So 1 minus x squared over 2 plus x to the 4th over 24, and we will expect to see that we get minus x to the 6th over, and then 120, right? Because, that would be, actually, sorry, this would be 720, because that's 6 factorial. and so on. And what do you notice? Well, actually, this is, we're getting all even powers, cosine is even, so it's evidently cosine of x. This is cosine of x, which is really interesting. So, okay, so that's a start, but we have to add on the imaginary part. So what happens if we add on the imaginary part? So we'll put this in parentheses. We'll add on, well, what do we get here? And then we'll multiply by I. X, we get x minus x cubed over 6. And then here we'll get plus x to the 5th over 120, and so on. And then we get an I here. Okay, well, what do you notice? This is cosine of x, right? All the odd powers over all of the odd factorials here. This is cosine of x. So this piece here is cosine of x. And this piece here is sine of x. So we have kind of, maybe not formally, but it's a pretty good, pretty decent proof that proof of Euler's great formula, because we have just shown that this is equal to cosine of x plus I sine x. And as I mentioned in the previous video, usually we denote the x here as theta, so it's more clear. So in other words, if we just plug in theta instead of x, get e to the I theta equals cosine theta plus I sine theta. And we are done. And pretty sure I mentioned this in the previous video, but to get the famous form of this, if we plug in theta equals pi, we had e to the I pi equals cosine of pi is -1, and sine of pi is 0, so this goes to 0. So we get that e to the I pi plus 1 equals 0. And that's the famous Euler's identity. So I hopefully you enjoyed this video. This wasn't that long, so it was a short one, but it was just a quick continuation of the previous video. So hopefully you enjoyed, and that's it for today. Goodbye.